Hi everybody. So the first video today is going to look at one final example of quantization, and again this is related to the electrons inside atoms, but this time we're not looking at energy quantization. In fact, we're looking at quantization of what's known as the magnetic moment. And this was first tested and seen through an experiment called the Stern-Gerlach experiment. So in this video I'm going to briefly describe what the atomic magnetic moment is, where it comes from, and how this is tested in the Stern-Gerlach experiment. Okay, so if we just briefly review what we saw last time with the Bohr model of the atom. So the Bohr model of the atom is very similar to Rutherford's idea. You have a nucleus which is very much heavier than any of the electrons, and therefore it is more or less stationary, and in the classical picture the electrons go around this nucleus in orbits like this. Okay. So here's an electron going around. Okay. But we saw in that video there's a lot of evidence that the energy of the electrons is quantized, and we saw an explanation for that using the de Broglie wavelength and the idea that the distance from the nucleus is also quantized. So this Bohr model actually, as well as giving you quantization of energy, it tells you that various other properties of these electron orbits are quantized. So as well as having energy, we also have quantization of orbital radius. Okay, we actually saw that in the derivation. We also have quantization of momentum, because we saw the momentum of the electron is related to its orbital radius in this example. Okay, so I will just say that although the Bohr model gets the quantization of energy for hydrogen exactly right, well, you know, very nearly exactly right, it doesn't get the quantization of radius and momentum completely correct. Okay, and this is because the Bohr model came before the full quantum theory was developed, and the full quantum theory says something different about position and momentum measurements, which we're going to talk about in the very last video of this week. Okay, so the Bohr model says these three things are quantized. The full quantum theory says yes, energy is quantized, but radius and momentum are not quantized in this way. Anyway, so the point of the Stern-Gerlach experiment was to test that, another way of testing this quantization basically. Because the electron is going around the nucleus, it creates a current going around the nucleus, an electrical current, and you should know from electromagnetism class that when you have an electrical current flowing, you will get a magnetic field. Okay. And this magnetic field gives rise to what's called the atomic moment, the atomic magnetic moment of the atom. So if I just write that, okay. So you have orbiting electrons. So these give rise to electrical current. And this gives rise to a magnetic field. Okay, for example, if you know Maxwell's equations, which are the equations of electricity and magnetism, which if you haven't seen yet, you will see in the third year, I think. Then one of Maxwell's equations says the following: the curl of the magnetic field in a system must be equal to some constant times the current flowing around the system plus the rate of change of the electric field. Okay, so in the system here, because we have flowing current, we must also therefore get a magnetic field from this equation. Okay, what does this magnetic field look like? So we have, if the electron is moving around this way, because the electron is negatively charged, that gives rise to a current flowing in the opposite direction. and the magnetic field arising from such a current looks like this. I'll do magnetic field in green, I guess. Okay, you get magnetic field lines that flow around like this. Okay, I'm sure you've all seen diagrams like this before. Okay, and the direction of the arrows is this way. Okay, so this is what's known as an electric dipole, such a magnetic field. Sorry, a magnetic dipole. Okay, and magnetic dipoles can be quantified by a single vector, which is known as the magnetic dipole moment, or just the magnetic moment. Okay, so full name is magnetic dipole moment, but often the dipole is dropped. And this is usually given the symbol mu or m. Okay, and it's a vector, and the way it's defined is if you go to the center of the loop and look at what the magnetic field lines are doing, then it goes parallel to the magnetic field lines in the center like this. So that's the magnetic dipole moment, or the magnetic moment. And as I said, because these atoms have electrons flowing around them, they will get a magnetic moment like this. Okay, right, so what the Stern-Gerlach experiment wanted to test is if these magnetic moments were also quantized. Okay, and it was tested using a magnetic field, because if you have a magnetic moment and you put it into an external magnetic field, then you get forces generated. So forces on a magnetic moment in a magnetic field Okay, so let's say B is here the external magnetic field you apply the magnetic moment to. So you have, well, we chose green, right? You have some external magnetic field like this. This is B, and in this field I have a magnetic moment, mu, like this. Okay, and there is a force on the magnetic moment because of the magnetic field. Okay, and the equation is given as follows. The force on the magnetic moment is given by magnetic moment dot the gradient operator applied to the magnetic field. So if you haven't seen this gradient operator before, let me just write this out in components. This is x component of magnetic moment times the derivative with respect to x, and then the same for y and z. So all of that describes a differential operator, and you apply that to magnetic field B. Okay, so one thing you can see from this equation is that if the magnetic field is constant, then the force is going to be 0, because here you have derivatives. So if B is a constant, each derivative will just give you 0, and therefore the total force will be 0. Okay, so you don't want that. So that means you have to create a magnetic field which is not constant in space, I mean. In other words, the magnetic field should change as a function of position. Now let's suppose that in our experiment we are interested in measuring the z component of of the magnetic moment. Then in that case we need to have a field such that dB by dz will give us a constant term. Okay, so suppose We want to measure mu z. Okay, so in order to do that, we need that dB by dz, okay, should be a non-zero constant, just constant so we know how big it is. Okay, and because we don't want to measure mu y or mu x, we want the other derivatives to be approximately equal to 0. Okay, so you can't actually get a magnetic field where this is exactly true, where these two derivatives are 0 and this one is not, but you can get something which is approximately right, as follows. Okay, so let's suppose I take two permanent magnets like this, and let's suppose I put the north pole of the magnet on one side and the south pole of the second magnet on the other side. Then, as you all know, you will get a magnetic field between the two poles like this. Okay, but this one is not good because here in the middle between the two magnets, the magnetic field B is approximately constant. Okay, and that you don't want because then you won't get a force on the magnetic moment. So instead, what Stern and Gerlach did, I think one of them suggested the experiment and the other one actually performed it. I can't remember which way around it was. Anyway, they had funny shaped magnets. So they had the north pole of the magnet having a sharp edge like this, and they had the south pole of the other magnet having a curve like this. Okay, so I'm going to need this picture for later, so let me just copy it over here for now. Okay, so if you do that, then you actually get a magnetic field between the north and south poles that looks more like this. Okay, and here if I look in the center here, then I get approximately what I want. Okay, I get that most of the field is aligned in the z direction, and dB z by dz is approximately equal to a constant, and the derivatives in the x and y directions are not so big. Okay, although they can't be exactly 0, but they're not so large. Okay. So that's what they did in the experiment. They designed permanent magnets which have a magnetic field that looks like this, shown in green here. And now I can describe the full experiment for you. Okay, so you align the magnet in 3 dimensions, so it looks something like this. So this is the north pole here, this is the south pole here. Okay, and you take a stream of atoms. So okay, they were gold atoms, so sorry, they were silver atoms, so I will use a silver color for the atoms. Okay. Okay, and you push these atoms through the magnetic field generated by these magnets here. Okay, and what do you expect to happen? Well, if the magnetic moment on one atom, say this first one, is pointing up like this, then you see that the force from the formula up here, this dB by dz, the magnetic field is increasing as you move up, so that's a positive number in the z direction, and mu z is positive as well, so that will give you a force in the z direction going up. Okay, so here when the atom moves through these magnets, it will have a force on it in the z direction going up here, and that will cause it to curve upwards like this. Okay, if I were to take a second atom which has a spin, a magnetic moment pointing in the opposite direction, then this will have exactly the opposite force, and therefore when it passes through the experiment it will start to curve down like this. Okay, and if I have a atom with a magnetic moment somewhere in between these, then it will go have a force somewhere in between these two extremes, so you will get a beam of atoms going out like this. So at the end of the experiment, you put some kind of detecting screen here, and you measure where the atoms impact the screen, and what you expect to see is a line like this corresponding to the different possible values of the magnetic moment. Okay. Okay. But the reason the Stern-Gerlach experiment is famous is that this was not the result that was actually obtained. Okay. So the final thing is to explain what was the actual result. So I just need a little bit more space. That's weird. Why did that move? Okay. Fine. Okay. So that was the expected result, but the result that was actually obtained appeared like this. I have the silver atoms here, and when they go through, instead of getting a range of different values, only two are found. Half the atoms curve up by a fixed amount, and half of the atoms curve down by a fixed amount. So when you look at the result of this, what you get on the screen, instead of a line like this, you just get 2 points. Okay. And this means that you have only two possible values. This is the actual result of the experiment. Okay, so the expected result was that you have a continuous range of values, whereas the actual result is that you have only a discrete set, in this case 2. Okay, so this is another example of quantization. Instead of having a continuous range, you only get a fixed set of points, and this one is quantization of the z component of magnetic moment. The quantization of uc. Okay. Right, so this result is very strange, and the reason it's strange is there's absolutely nothing special about the z direction, right? When you prepare the atoms, they don't know which direction z is, so in principle their magnetic moments will be all over the place. But it turns out when you do the experiment, half of them choose one mu z value and half of them choose a different mu z value, and you end up with 2 points like this. So then you might ask, well, what about their components in other directions, right? What happens if you tried to measure the magnetic moment in the x direction or the y direction, which you can do in the same experiment, just putting your magnetic field in a different plane, right? And it turns out that whichever direction you measure the component of magnetic moment in, you always get exactly the same 2 points at exactly the same positions. And this is something which has no classical explanation, and in the next video I'm going to say what the quantum explanation for this is, although I can't give you the full details without going too deep into the quantum mechanics. But I will at least explain the basic ideas of how we can understand this very strange result. Okay, so the last thing I want to do in this video before I finish is relate the magnetic moment here to the angular momentum, because they are related quantities. That's very weird. These always shift when I change the canvas size. I don't know why that happens. There we go. Okay, so last part, relation to magnetic moment, relationship of the magnetic moment to the angular momentum. Okay, so if we look at the magnetic moment above, we have a current I going around, okay, and it's going through a unit of area A, okay, and the formula for the magnetic moment in such a case is that it's equal to the product of I times A. So a bigger area gives you a bigger magnetic moment, a bigger current gives you a bigger magnetic moment. Okay, kind of makes sense. But we can work out what this is for the atom, because for the atom we imagine that this is a single electron at radius r moving around this direction in speed v. Okay, so then the area is simply going to be pi times the radius squared. Right, that's the area of the circle. And the current, so this is charge per unit time, right? And the charge on the electron is E. And the time it takes to go round is, or per unit time, so 1 over the time, is speed divided by the distance it travels. So that's v divided by 2 pi r. Okay? So if you put those two together, you see that this pi's cancel, one of the r's cancel, and you get E times V times R divided by 2. Okay, so this you can rewrite as E divided by 2m times m times V times R. And the reason you do this is that this is simply the angular momentum L of the electron. Okay, so in other words, you get that the magnetic moment is equal to charge divided by twice the mass times the angular momentum. And angular momentum is a vector, magnetic moment is a vector, and these two vectors both point in the same direction, which is this way as I've drawn it here. Okay, so we get that mu is equal to, well, in fact there's a minus sign because the charge on the electron is negative, but okay, the vectors point in the same direction. Okay, so what this means is that quantization of the z component of magnetic moment is the same as quantization of the z component of angular momentum. Okay, so in the next video I'm going to talk about quantization of angular momentum in more detail. Okay, so that's where we'll finish this.